The paper of the day is right behind logging. The design of the logging and recovery components of database management systems has always been influenced by the differences in the performance characteristics of volatile and non-volatile storage devices like SSD, and SSDs. The key assumption has been that non-volatile storage is much slower than DRAM and only supports block-oriented read writes. But the arrival of new non-volatile memory, NVM in short, storage that is almost as fast as DRAM with fine-grained read writes invalidates these previous design choices. This paper explores the changes that are required in the DBMS to leverage the unique properties of non-volatile memory in systems that will still include volatile DRAM. They make the case for a new logging and recovery protocol called write-behind logging that enables a DBMS to recover nearly instantaneously from system failures. The key idea is that the DBMS logs what parts of database have changed rather than how it was changed. Using this method, the DBMS flushes the changes to the database before recording them in log. Their evaluation shows that the protocol improves the DBMS's transaction throughput by 1.3 times, reduces the recovery time by more than 2 orders of magnitude, and shrinks the storage footprint of the DBMS on non-volatile memory by 1.5 times. To evaluate their approach, they implemented it in the Peloton in-memory DBMS and compared it against write-ahead logging using 3 storage techniques: NVM, SSD, and HDD. These experiments show that write-behind logging with non-volatile memory improves the DBMS throughput by 1.3x, while also reducing the database recovery time and the overall system storage footprint. The results also show that write-behind logging only achieves this when the DBMS uses NVM. The DBMS actually performs worse than write-ahead logging when write-behind logging is deployed on the slower block-oriented storage devices, example SSD and HDD. This is expected since the protocol is explicitly designed for fast, byte-addressable NVM. In terms of benchmark, the paper uses 2 benchmarks: YCSP, which is a widely used key-value store workload from Yahoo. It is representative of the transactions handled by web-based companies. The workload consists of 2 transaction types: a read transaction that retrieves a single tuple using its primary key, and update transaction that modifies a single tuple based on its primary key. The second is TPCC. This benchmark simulates an order entry application of a wholesale supplier. The TPCC workload consists of 5 transaction types, of which 88% of them modify the database. They configured the benchmark to use 8 warehouses and 100,000 items. The initial storage footprint of the database is 1 gigabytes. Looking at the contributions, this paper presented the write-behind logging protocol for emerging non-volatile storage technologies. They examined the impact of this redesign on the transactional throughput, latency, availability, and storage footprint of the DBMS. Their evaluation of the recovery algorithm in Peloton showed that across different WorldTP workloads, it reduces the system recovery time up to 100 times and shrinks the storage footprint by 1.5x. Let's talk PS score for this paper. Overall, this paper is a decent read, so it gets 9 out of 10 on readability. With 12 pages long, it scores 8 out of 10 on length. It's a research prototype with an implementation in a research project with pretty good description, so that makes it 8 out of 10. Its industry value and nulling meter is high, so it gets 8 out of 10 on each, with overall PS score of 8 out of 10.